Hey everyone, welcome back. This is week 17. So this week I finished sections 4.5 and 4.6 of Boyd, which are mainly about two things, geometric programming and then a broader sort of framework called the Generalized Inequality Constraints, which is where the semi-definite programming lives. So these sections were a little different from what we've been doing. The main theme here is that these problems, they don't look convex at first, but they actually are, either from change of variables or for something else. So let's get into it. Before we talk about geometric programs, we need two definitions. A monomial is a function of the following form, where c and any of the exponents can be real numbers, but c is positive. So, for example, something like x to the 1/2 times y to the -3 is a monomial. A polynomial is just the sum of monomials. So for polynomial, we just take the sum of the monomials here. Some key properties about these functions is that polynomials are closed under addition, multiplication, and non-negative scaling, and monomials are closed under multiplication and division. Okay, now we can talk about a geometric program. So a geometric program is the following. So here, each of the fi's are polynomials, and then the hi, the equality constraints, are monomials. And then we also have the implicit constraint that x is positive, or living in R-Van space. Now the question is this problem a convex optimization problem? And the answer is not obvious, but this is kind of the whole point of this section. So if we take the log of all the x values, because we have all these exponents in the exponents, so why don't we take the log? And so once we take the log transform with this new variable y, we have this expression here. And so now we're working in the log space. So let's see what happens to the monomial under this substitution. So we can see here, substituting each xi for e to the power of yi into the monomial equation, we see that the monomial becomes an exponential of an affine function. So we know this is convex. Exponential affine is convex. Now let's look at the polynomial, which is the sum of monomials. This is the same idea, just take the sum here. And so this is the sum of exponentials of affine functions. So you've probably seen this before. This is related to the log sum exponent function. And like before, that's still convex. So after taking this change of variables, if we also take the log of the objective and the constraint functions, the geometric problem becomes like this. So the objective and the inequality constraints are log sum exponent functions. So those are convex. And the inequality constraints, the equality constraints here are also affine. So in total, this entire problem is a convex optimization problem. This is called the convex form of the geometric program, as opposed to the polynomial form. And also another key thing to note is that no computation is really needed to transform between them. The problem data is literally the same. All the information is stored between each form. It's just purely how you represent the problem. Another nice observation is that if every polynomial in the problem has only one term, so everything's monomial, then the log sum exponent collapses to just an affine function, and the whole thing reduces to a linear program. So the geometric program is a strict generalization of linear programming. Okay, so now section 4.6. So 4.6 asks, what if instead of scalar inequalities, f of I x is less than or equal to 0, we allow vector valued constraint functions with generalized inequalities? So the standard convex problem looks like this, right? We're trying to minimize some objective function subject to these constraints. But now what if we generalize this inequality in these inequality constraints here? That is, what if we replace this inequality here with this generalized inequality, where k is a proper cone? So this is the exact same structure, but now f of I maps to r of ki instead of r. And the inequality is defined by the cone k. So the good news is that most of the results we already know still hold. Feasible and optimal sets are still convex, local optima are still global optima, and these problems can be readily solved, with standard convex solvers. The simplest special case is the conic form problem. So this is the conic form problem here. So we have a linear objective here. We have a single affine constraint function, one cone, so one cone k here. But notice when k is a non-negative orthant, or r van plus, so this is just a linear program. This just expands to n linear inequality constraints. So conic programs are LP with component-wise inequality swapped out for cone inequality. Now let's look at another important special case in practice. So first, let K here be the positive semi-definite K by K matrix set. Then the conic form problem becomes a semi-definite program. So here's a semi-definite program here. So G and F1 through F of n are symmetric matrices. And the constraint here is often called the linear matrix inequality. The reason is, well, it's a linear combination of matrices. So it's linear in X, but the inequality is over a positive semi-definite cone. Alrighty, so that's 4.5 and 4.6. The two big takeaways for me this week is first, geometric programs are a case where a simple change of variables, aka log substitution, turns a non-convex looking problem into a convex one. The second takeaway is that semi-definite programmings are LPs, or linear programmings, big sibling. So the move between component-wise inequalities to matrix inequalities, really opens a huge class of useful problems. So I'll see you next week.